If you asked a machine to draw a single straight line separating true from false, and it mathematically just, well, it couldn't do it. You wouldn't just throw away the machine.
Right. You'd invent an entirely new dimension for it to think in.
Exactly, you'd invent a new dimension. And that mathematical failure is really the exact reason deep learning exists today. So, welcome to this deep dive.
Yeah, glad to be here.
Today, we are looking at a stack of graduate course notes, modules, and some summaries covering lessons 1 through 5 of a course on deep learning and neural networks.
And our mission here, just for everyone listening, is to bypass the really basic 101 definitions.
Yeah, we're not doing a dictionary read.
Right, exactly. Like, you already know the basic differences between AI and machine learning. Today, we're going to deconstruct the actual mechanical reality of these systems.
The gears.
The gears, yeah. We want to serve up a conceptual reminder of the foundational ideas that prepare you for advanced AI topics. We're focusing entirely on how an empty, mathematically sterile architecture actually learns to, perceive the world.
So, to you listening, expect us to really get into the weeds today. We are going straight for the underlying logic of how and why modern machine learning systems actually function.
It's going to be fun.
It is. But before we even talk about layers or networks, the sources isolate 4 non-negotiable components required to make literally any machine learning engine run.
Right, the 4 pillars.
Yeah. Data, the model, the objective function, and the optimization algorithm. Okay, let's unpack this. I was trying to map this to something intuitive, like a student preparing for a notoriously grueling final exam.
Oh, I like that. Let's hear the translation. How are you mapping those 4 components?
Well, the data is basically the stack of practice exams and the textbook.
Okay, sure.
The model is the student's actual brain, like the literal neural pathways being formed to map the questions to the answers.
Right.
Then the objective function, or the loss function, is the brutal grading rubric. It's the metric that tells the student exactly how badly they failed the practice test.
Which they usually do on the first try.
Oh, massively. But the optimization algorithm, and this feels like the most critical part, that's the specific study strategy the student uses to adjust their understanding, so they get a lower error rate on the next attempt.
The analogy holds up surprisingly well, honestly, because
Yeah.
it really highlights the iterative nature of the loop. Like, a model doesn't just look at data and instantly understand it. It takes time.
It's a process.
Exactly. The optimizer is actively tweaking the internal parameters of the model to reduce the penalty defined by that objective function.
Hmm.
And, the way that quote-unquote student learns takes different forms depending on the paradigm we set up.
Yeah, the notes detail supervised, unsupervised, and reinforcement learning.
Right.
Supervised is having the answer key. Unsupervised is looking for hidden structure and completely unlabeled data. And reinforcement is trial and error with a reward system.
Pretty much.
But let's set the paradigms aside for a moment because I really want to look at the model component itself. How do we actually build the brain?
Well, it starts simple.
Right. The course starts with linear regression, which is essentially just computing a weighted sum of input features plus a bias term to make a prediction.
And that simple statistical formula, weights, features, and a bias, is the exact mathematical structure inside the very first artificial neuron.
Wait, all the way back in the 50s?
Yeah. In 1950, Frank Rosenblatt introduced the perceptron. It's a single neuron binary classifier.
Single neuron.
Just one. It takes your features, multiplies them by the weights it has learned, adds a bias, and then passes that result through an activation function.
And that activation function is just the threshold for a decision, right? Like it decides whether the neuron fires or doesn't fire.
Exactly. Cat or not cat.
True or false.
Yep.
But this brings up a massive question for me. If a single artificial neuron, this perceptron, can take data, learn weights, and make binary classifications using that math, why did we ever move past it?
What do you mean?
Well, why build networks with a trillion parameters today if the math of a single neuron works perfectly fine?
Because it fails spectacularly on anything remotely complex.
Really? Just hits a wall.
A huge wall. The mathematical limitation of a single neuron is that it can only learn linear decision boundaries,
Meaning what, exactly?
meaning it can only draw a perfectly straight line through your data. If your data cannot be separated by a straight line, the single perceptron is entirely useless.
Oh, this is the XOR problem mentioned in the notes.
Yes, the XOR problem, exclusive OR.
Right.
It's a basic logic gate where the output is true only if the two inputs are different. If you plot that on a graph, it is mathematically impossible to draw one single straight line to separate the true states from the false states.
Because the relationship is nonlinear.
Exactly. A purely linear classifier just hits a wall. To solve that, to model nonlinear relationships, you are mathematically forced to add hidden layers.
So it's not that computer scientists just, wanted to build something that looked like a biological brain just for the fun of it.
No, not at all.
They literally hit a mathematical wall where a single neuron could not compute basic logic. And that limitation is what forces us into the realm of deep learning. We just have to stack these neurons.
Yeah, that leads directly to the multilayer perceptron, or the MLP, which the course notes call the hello world of deep learning.
A hello world. I love that.
You have an input layer to receive your features, hidden layers to do the processing, and an output layer for the final prediction.
The hidden layers are what fascinate me, though, because every single neuron in those hidden layers has its own activation function.
That is the secret sauce.
Yeah.
Those activation functions in the hidden layers are what inject nonlinearity into the entire system.
Because they're firing or not firing at different times.
Exactly. Because you have multiple layers applying nonlinear transformations one after another, your model is no longer restricted to drawing straight lines.
It can bend.
It can warp, bend, and fold its decision boundaries to wrap around incredibly complex data patterns.
But, when we look at massive modern networks, things like GoogleNet or Inception from the computer vision case studies and the sources, we aren't just sitting there coding a million individual neurons.
Oh, definitely not.
The architecture has to be more structured than that.
Yeah, deep neural networks are highly hierarchical. We don't think in terms of individual neurons anymore.
Okay.
Neurons form layers. Layers are then grouped into reusable engineered blocks.
Like Legos.
Sort of like Legos, yeah. And those blocks form the complete models. Advanced architectures rely heavily on these repeated block patterns or motifs that have been empirically discovered to perform well for specific tasks.
So you're snapping together complex pre-engineered blocks to build the architecture. But what are those blocks actually doing to the data? Because the notes spend a lot of time on this concept of representation learning. And I want to push past this standard explanation here.
What's fascinating here is that representation learning is arguably the most profound concept in the entire course.
Really? The most profound?
I think so. Deep learning isn't just about writing a task-specific algorithm. The hidden layers of a deep network are learning increasingly useful, complex representations of the data all on their own.
Okay, let's visualize how that actually works mathematically, because it's not just a filter looking for a shape.
No, think about the geometry of the data. Imagine a crumpled piece of paper.
Okay, crumpled paper. Got it.
On that paper, there are red dots and blue dots completely mixed together in the folds.
Right.
A single neuron, our simple linear classifier, is trying to take a sword and slice that crumpled paper with one perfectly straight cut so that all the red dots are on one side and all the blue dots are on the other.
Which is impossible.
Completely impossible.
Because the paper is too tangled.
Exactly. The hidden layers in a deep network act as a series of transformations that slowly unfold the paper.
Unfold it.
Yeah. The first hidden layer stretches the space a little bit, the next layer twists it, the next layer flattens a fold. By the time the data reaches the final output layer, the network has warped the underlying geometry of the space so thoroughly that the red dots and blue dots are neatly segregated.
That's crazy.
And then that final output layer just makes one simple straight cut.
That is incredible. The network is basically learning how to represent the data in a new dimension that makes the final task totally trivial.
Yes.
It's bending the universe the data lives in. But wait, if I stack all these hidden layers together to unfold this paper, how does the network actually know which layer should pull left and which layer should flatten a fold?
Right. Who's in charge?
Yeah, who is directing that traffic? Because an architecture, no matter how elegant, is essentially an empty, useless shell until it figures out the correct weights and biases to make those transformations happen.
The traffic director is the optimization algorithm.
Yeah.
And to understand how it directs traffic, we really have to isolate a critical vocabulary distinction.
Which is?
Parameters versus hyperparameters.
Well, this is a trap a lot of people fall into.
Very often.
If the network is learning on its own, what is the human engineer actually doing? Are we just setting the boundaries?
That's a really good way to frame it. Parameters are the internal values the model learns entirely on its own during training.
The millions of individual weights and biases.
Exactly. Hyperparameters, on the other hand, are the architectural and strategic settings the human engineer chooses before training even begins.
Like what?
Things like the learning rate, the batch size, the number of epochs to train for, and vitally, which optimizer to use.
And the central optimization method the course focuses on is gradient descent.
Right.
The notes mention the goal is to minimize the loss function. But how does gradient descent actually locate the correct parameters?
Well, let's discard the usual visual metaphors for a second and think about it mechanically.
Okay.
Imagine you are calibrating a massive, complex soundboard with a billion different fader sliders.
A billion sliders. That's a big soundboard.
Very big. And you can't hear the music playing. The only feedback you have is a single, giant digital dial that shows the overall static noise level of the system.
Static.
Just static. Your goal is to get that static dial to zero.
So the static dial is the loss function.
Exactly. Gradient descent works by calculating the gradient, the mathematical slope or derivative of that static dial with respect to every single slider on the board.
So it's testing them.
Basically, it essentially asks,
Yeah.
if I nudge slider number 4,212 up by a fraction of a millimeter, does the static increase or decrease?
Oh, wow. And it does that for all of them.
It computes this for all billion sliders simultaneously.
Mm.
Then it adjusts every slider a tiny bit in the direction that decreases the static. That is one single step of gradient descent.
And the size of that nudge, like how far you push the sliders in one go, that's dictated by the learning rate, right? Which is one of those human-chosen hyperparameters.
You got it.
Because if the learning rate is too small, you're nudging the sliders by microscopic amounts, and it takes months to tune the board.
Too slow.
Right. But if it's too large, you shove the sliders so hard, you blow out the system and the static just spikes.
Right. Finding the Goldilocks learning rate is a massive part of the engineering challenge. And it's complicated by how much data you feed the optimizer before making an adjustment.
Which is where the different flavors of gradient descent come in. The sources break this into 3 distinct types.
Yeah.
Full batch gradient descent is the first one. That's where you calculate the slope using every single example in your entire dataset before moving the sliders even once.
Which gives you a highly accurate calculation of the true gradient. But, if you have 10 million high-resolution images, calculating the gradient across all 10 million just to take one tiny step is computationally agonizing.
It's just way too slow.
Exactly. So on the opposite extreme, you have stochastic gradient descent, or SGD.
Right. SGD looks at a single example, one image, one data point, and immediately updates the entire soundboard.
Which is blisteringly fast, but wildly erratic.
Because of the noise.
Yeah. Because one image of a cat might have weird lighting. So the gradient it calculates is highly specific to that one image, not cats in general.
So it's bouncing all over the place.
The path towards zero static becomes a jagged, noisy stumble. But surprisingly, that noise can actually be a mathematical advantage.
Wait, really? How is noise an advantage?
It can jolt the optimizer out of shallow valleys, what we call local minima, preventing it from getting stuck in a suboptimal state.
Oh, that makes sense. But the industry standard, the middle ground, is mini-batch gradient descent, right?
Yep, mini-batch is the workhorse.
You look at a small batch of examples, say 32 or 64, you average the gradient, and then update.
It balances the computational efficiency, gives you a stable trajectory, and critically, it allows for vectorized tensor operations, which are perfectly optimized to run on modern GPUs.
Okay, here's where it gets really interesting, though. If standard gradient descent works, why did we need to invent advanced adaptive optimizers? Because the course notes put a massive spotlight on an optimizer called Atom. What problem does Atom solve that standard gradient descent just can't?
Okay, so standard gradient descent applies the exact same learning rate, the same size nudge, to every single parameter.
Right.
But what if one parameter needs a massive adjustment, while another parameter is already perfectly tuned and just needs fine, delicate tweaks?
Oh, standard gradient descent just treats them identically.
Exactly. ADAM, which stands for Adaptive Moment Estimation, solves this by giving every single parameter its own custom, continuously updating speed limit.
That sounds impossibly complicated. How does it calculate a custom speed limit for a billion different parameters on the fly? The notes mention it combines the ideas of momentum and RMS prop, estimating first and second moments of gradients. But let's strip away the textbook jargon. What is the actual mechanic there?
Sure. So ADAM doesn't just look at the current slope. It looks at the historical behavior of the gradient. It tracks momentum, which is the first moment. If a slider has been consistently moving up for the last 100 steps, ADAM says, great, let's accelerate that slider in that direction. It builds up speed.
Like a snowball rolling downhill.
Exactly. But it also tracks the second moment, which you can think of as the bumpiness or variance.
The friction.
Yes, the friction. RMS prop acts as a friction mechanism. If a slider is fluctuating wildly, jerking up and down chaotically with every batch, Adam looks at that high variance and applies the brakes to that specific slider.
Oh, wow.
It dampens the learning rate for volatile parameters while accelerating the learning rate for consistent parameters. The result is an incredibly robust optimizer that handles noisy data and sparse gradients beautifully without the human engineer having to manually tune individual learning rates.
That is just a brilliant piece of engineering.
It really is.
But even with Adam acting as the ultimate traffic director, optimization is still notoriously difficult, especially as the networks get deeper. The notes dedicate significant space to the vanishing gradient problem.
Oh, the vanishing gradient. It's a mathematical tragedy, really.
A tragedy.
Well, mathematically speaking, when you use the backpropagation algorithm to update a deep network, you are using the chain rule of calculus. The error signal, the static level from our soundboard, has to travel backward from the final output layer, layer by layer, all the way to the input layer.
Think of it like a whisper being passed down a line of 100 people in the game of telephone.
That's a great way to visualize the chain rule in this context, because the activation functions often squash the values, say, between 0 and 1. Every time the whisper is passed to the next layer backward, it gets multiplied by a small fraction.
Because it's quieter.
It shrinks exponentially. By the time that error signal reaches the early layers, the gradient is effectively 0. The whisper is completely silent.
So the early layers receive no feedback whatsoever. They literally stop learning.
And if the early layers don't learn those fundamental representations like stretching the paper initially, the later layers have nothing useful to build on.
Because the foundation is broken.
Exactly. This is a massive issue in recurrent neural networks dealing with long sequences of text or time series. Getting a deep model to train it all, keeping those gradients flowing, is a massive mathematical achievement.
This raises the ultimate question of the course, I think. If our Atom Optimizer does its job flawlessly, if we completely avoid the vanishing gradient problem, and we drive our loss function on the static dial all the way down to absolute 0, does that mean our deep learning model is perfect?
No.
No.
And grasping why is perhaps the biggest conceptual hurdle in the entire deep learning field.
Okay, lay it on me.
There is a fundamental, almost cruel contradiction at the heart of machine learning. The goal of the optimizer is to minimize empirical risk on the training dataset, to reduce the training error to 0.
Right.
But the goal of the deep learning system is to achieve low generalization error on unseen data.
Optimization versus generalization, the central tension.
Exactly. A model can perfectly optimize the training objective and still be entirely useless in the real world.
We call that overfitting. Returning to our student analogy earlier, it's like the student didn't actually learn the underlying concepts of the subject. They just memorized the exact questions and answers in the practice exams.
Right, they memorized the noise.
They memorized every little quirk, typo, and piece of noise in the textbook. So they get a 100% on the practice test. But when you hand them a final exam with brand new questions they've never seen, they just fail miserably.
The model adapted too well to the training examples, mapping the noise instead of the signal. The course uses a Kaggle case study on house price prediction to demonstrate the rigorous workflow required to fight overfitting.
Right, because you cannot just throw all your data into the optimizer.
Oh, absolutely not.
You have to orchestrate a very strict data pipeline.
The workflow demands train test splits. You hold back a significant portion of your data in a vault. The model is completely blind to it during the training phase.
It never sees it.
Never. You also use validation data during the active training loop to monitor performance. If the training loss is dropping, but the validation loss starts rising, the model has begun memorizing.
It's overfitting.
Exactly. And you have to halt the training immediately.
The sources also emphasize standardizing numeric features and dealing with missing values in that Kaggle dataset, and then using k-fold cross-validation.
Which is incredibly important.
Yeah, that's where you partition the data into k different chunks and train the model multiple times, rotating which chunk acts as the validation set.
Right. It gives you a much more robust, statistically sound estimate of how well the model is actually generalizing, rather than just getting lucky on one specific test split.
So it's basically making sure the student didn't just get an easy test.
Precisely. All of these techniques, cross-validation, early stopping, standardizing features, are crucial because we're trying to build an engine that survives outside the laboratory.
But even a model that passes all those rigorous internal tests, a model with a perfect k-fold cross-validation score, can still collapse in production.
Why? I mean, if it rigorously proved it could generalize to unseen test data, what breaks it in the real world?
Well, if we connect this to the bigger picture, it's production data distribution shifts.
Distribution shifts.
Yeah. The test data you used, no matter how carefully you partitioned it, was drawn from the exact same historical population as your training data.
Okay, sure.
But the real world is entirely dynamic. What if consumer behavior fundamentally changes? What if a new piece of camera hardware alters the pixel distribution of the images?
Or what if massive economic factors instantly rewrite the rules of the housing market?
Exactly. The test changed, and the student is relying on representations built for a world that no longer exists.
The data the model encounters in production no longer looks mathematically like the data it was trained on.
Yep. The crumpled paper folded itself in a completely new way, and the model's straight line cut is now entirely in the wrong place. Man, bringing this all together, this deep dive makes it abundantly clear that deep learning is far more than just stacking massive layers of artificial neurons and throwing compute power at them.
It really is an art.
It's an incredibly delicate, highly orchestrated mathematical balancing act. You have to design a hierarchical architecture capable of learning complex geometric representations of data. You have to push it through a mathematically treacherous optimization process without the gradients vanishing.
Right.
And you have to constantly guard against overfitting to ensure the engine actually generalizes to a chaotic real world.
It forces you to respect the sheer engineering required to make these systems function at all.
Absolutely. As we wrap up this conceptual overview of lessons 1 through 5, the course modules leave the graduate students with a highly specific reflection question, and I want to pose it to you listening right now. When a deep neural network succeeds, how much of that success comes from the data, the architecture, the objective function, the optimization process, and the learned representation?
It's a profound question because they're all inextricably linked. You cannot have the representation without the architecture, and the architecture cannot learn without the optimizer traversing the objective function based on the data.
It's all one machine.
It is. And I will leave you with a final thought to mull over, building on that concept of production data distribution shifts.
Okay.
We spend immense amounts of time, energy, and computational power optimizing our models to perfectly represent the static data of the past.
Right.
But how do we build architectures that remain resilient when the fundamental rules of the environment and the data itself suddenly change tomorrow?
It really makes you realize that an AI isn't an impenetrable box of magic. It's an engine, a meticulously designed, fragile, incredibly powerful engine that we are still figuring out how to steer. Thanks for joining us on this deep dive.